Good. So am I audible, Anton? Are you able to hear me?
Yes, you are audible.
Okay, great. Thanks. So uh, we started with these different translations, right, across different kinds of automata. Like when I say different kinds of automata, like these were automata with different acceptance conditions. Uh, so we looked at generalized Büchi automata to Büchi automata, right? And we also talked about different kinds of translations. Like the first kind was like you just, yeah, the accepting condition, the alpha, you sort of like you look at it in a different way, you interpret it in a different way. And then we also talked about something called typeness, where the acceptance condition, it depends on the structure of the input automaton. And then the final and the more general class of translations where we are allowing the state space to be modified, right? So that's what we did when we did the translation from uh, generalized Büchi to Büchi. And we also looked at non-deterministic Rabin to non-deterministic Büchi automaton. So could you try to recall like what we did when we went from Rabin to Büchi automaton? What was the idea? So what was the Rabin acceptance condition? What was the Rabin acceptance condition to start with? Right. Right. Alpha should be, there should exist one index I such that alpha is visited infinitely often and beta I should be visited finitely often, right? And how did we do the translation from non-deterministic Rabin to non-deterministic Büchi automaton?
So we created copies in such a way that so we'll go from one copy to the another after a point, and the new copy won't have the beta states.
Won't have the beta states, right? Yeah. So the and if you have multiple indices, like you have say k indices, then what we do, we essentially like take the disjunction. So we for a single index NRW, we get an NBW, and when you have k indices, we take the disjunction, right? And so the thing is, in the case of Rabin automaton, like this can be it can be considered to be the language can be considered to be the union over all these AIs, where I consider I is the ith alpha I beta I that pair, right? But so this is like a disjunction over this one index Rabin automaton. Now we also then we started looking at non-deterministic Streett automaton to non-deterministic Büchi automata, Büchi word automata translation. And what was the acceptance condition for Streett automaton? How does it work? What is the acceptance condition there?
Inside intersection, so that for all I.
Yes.
If the inside intersection alpha is connected,
right? So there is an implication here. For every I, if alpha I is visited infinitely often, then beta I is also visited infinitely often, right? And then just in the same spirit as the previous translation from NRW to NBW, we were also suggesting the following, that now can you do this, that you take one index non-deterministic Streett automaton and then translate it into non-deterministic Büchi word automaton, and then you take the intersection over all such one index NSW. So does it work?
Because it's like for a run that property is there, and
yeah.
when the intersection, it's for a word, not necessarily for the same.
Right. So it can happen, for example, so the acceptance condition in non-deterministic Streett word automaton is like there should exist a run which satisfies for every I. So the single accepting run should satisfy this accepting condition, where the accepting condition is like it should hold for every I. So for every pair alpha I, beta I, this run should satisfy the following condition. What is that condition? If alpha I visited infinitely often, then beta I should also be visited infinitely often by that run for all I, right? Now, if you consider it can happen, like if you do this intersection separately for every individual NSW with a single index, then it can happen that there can be a word which can have different runs. Let's say it has run R1 and R2, and if the NSW is, let's say, of index 2, you can say that R1 satisfies like the alpha 1 beta 1 condition, R2, which is a separate run which will satisfy alpha 2 beta 2 condition, and so the word will be both in that first NSW with the in the language of the first NSW with this with the pair alpha 1 beta 1. It will also be in the second NSW with the pair alpha 2 beta 2, and hence in the intersection it will be there, right? But that's what not we are looking for. This word should ideally not be there if there doesn't exist a single run which satisfies both alpha 1 beta 1 as well as the alpha 2 beta 2, this condition, right? So this approach doesn't work. Okay, so now we are going to see like what we can do. So one of the things like is that we can do the simplification if we can, for example, consider the whole NSW as a disjunction of simpler automata. Okay, so if you can do a disjunction of simpler automata, that's one approach to do it. But now it's like you have a conjunction, like in the sense that you have to satisfy this condition for all I. Can we now express this as a disjunction? So that's the thing. So so okay, so let's say we have something like this that we consider for, okay, so we have this alpha, it's of the following form, right? Like alpha 1 beta 1 to alpha k beta k. Now a run is accepted if, so this is the standard NSW, like this condition, right? It's this or this, which is that same as the implication. Now we are saying that let for I, which is a subset of k. What is k? K is the set from 1 to k. So this is nothing but the set 1 to k, right? So I'm just denoting it in this way. Square bracket. Now we are saying that we define an NBW AI that accepts all words W such that there is a run R of A on W, and this should satisfy the following condition, which is like for all I belonging to I, right? Inf of R intersection alpha I, this should be empty. So that means that alpha I, for all I belonging to I, alpha I should be visited only finitely often, and for all I in k minus I, right, the complement of I, this set, inf R intersection beta I should be this, should not be empty. So beta I should be visited infinitely often for all I which is in the complement set, complement of capital I, right? So let's see. Now let me try to. So this is, for example, what will happen here. Is it visible? Or maybe let me try to make it a bit larger. So I'm just considering a set where k is 2. A set where k is 2. Okay. So suppose your alpha is of the form alpha 1, beta 1, alpha 2, beta 2. So the I can be one of these things, right? It can be the empty set or 1 or 2 or 1, 2. Now, if I say I equal to the empty set, then a run R is accepting if this is the thing, right? Like the run R, it visits beta 1 infinitely often as well as beta 2 infinitely often. Clear? Right? So this is what we said. So we are defining the I. There are different possible, like 4 possible values of capital I that can be there. I can have different 4 such valuations. If I is the empty set, then a run is accepting if in the complement set, which means the complement set is 1, 2, and the run visits beta 1 infinitely often as well as beta 2 infinitely often. If I is 1, then the run is accepting if it visits alpha 1 finitely often and beta 2 infinitely often, like that. Okay. Similarly, I equal to 2, I equal to 1, 2. If I equal to 1, 2, then a run R is accepting if it visits both alpha 1 as well as alpha 2, both of them only finitely often. Clear? So the definition of the accepting run. Now, I have the following claim that LA is the union of LAI where I is some subset. Okay. So if I give you, let's say, k equal to 2, can you try to sort of prove that this is indeed true?
Because if there is an new word in LA, then that means there is some set of alpha I such that like the condition was either if our intersection alpha is empty or if our intersection beta is empty.
So what was the main condition? So there was a conjunction here, right? For all I, this or this. Okay. Now I am saying that the language of A is like the union over all these AI, where I is a subset of like 1 to k. Yeah.
So for any run, there will exist some set alpha I such that if our intersection alpha is empty, and for the remaining sets, it's like if our intersection beta is empty. So we can just split that.
So just have a doubt. If the same run has the property that for all I sets, right?
Yes.
Is that particular run? It's the same run that satisfies. It's not like there is a run for I is empty set.
So which one you are talking about? Like this one here?
In the example.
So
for I equals empty, we are taking one run for I equals the set of 1. It's a different run?
Yeah, it can be a different run. It can be a different run.
But above we are talking about a single run.
Exactly. Above we are talking about a single run. And here AI has this condition. AI has this condition like, so the alpha i's should be visited only finitely often, and the complement set for that beta i's should be, all the beta i's should be visited finitely often, infinitely often. Right? Right? So how do you, like, so now suppose if I say my set k is just 1, 2. So suppose if I have something like the following: alpha 1, beta 1, and alpha 2, beta 2, right?
So technically, if you take any of those, one of those four runs, like in the case K equal to, if you take any one of those four runs, the condition is still satisfied. The condition that you want, either infra intersection alpha is, okay, but it can have something.
So
like if we take any of those four runs that we have a run for which infra intersection.
So can you try to do the following? Like suppose my K is just 2. Okay. And then can we try to see like what is the language of A1 or like, sorry, what is the language of A empty set? Then what is the language of A1? What is the language of A2? And what is the language of A1, 2 like this? And if we take the union of all these four, then am I going to get like this, the LA?
Because
Right,
we have
because-
that one run
Ha,
that satisfies that property, and that is a property we want for the word to be in any.
I don't understand how.
So suppose we are taking set I is equal to one set.
Okay,
Then we have a run such that infra intersection alpha 1 is empty and infra intersection beta 2 is not empty.
correct.
So our required condition is either one infra intersection alpha I is empty or infra intersection beta I is not empty.
Right.
That is satisfied in this condition.
So, okay,
So if the word is there in AI,
yes,
you take the run that accepts it,
okay,
and that will still satisfy the condition that we require. So it is going to be in N.
okay. So you are saying that if this is accepted by, let's say, if there is a word which is here, then this word is also in this, accepting
That
this.
same run is accepted.
Same run is accepting there. But and what about the other way around? Like, can it have something beyond what
No,
this
because
have?
it has to be a subset, like wherever it's accepting.
Yeah.
The accepting set is alpha I accept non-empty intersection set.
Right.
It will be a subset of 1, 2.
Right.
So it's gonna be one of these i's. So it will be in one of these.
Okay, good. I think, sure. So the another way of just looking at it, you are right, is that, I mean, I can also think of, so for example, suppose I have these propositions, I can say that if, suppose inf of alpha, inf of some r, intersection alpha I, suppose this is not empty, okay? And then I'm saying inf of R intersection beta I, this is not empty, okay? I can call this maybe this proposition, let's say P, and this is Q, okay? Or PIQI, like this, right? So suppose now if I say A of phi, how am I going to represent this A of phi? So this is like negation of not, okay, so it's A of phi is just like, so I have Q1, Q2, right? So this is A of phi. It's just Q1, Q2, correct? And what about, and okay, sorry, am I saying it right? So I have, if this is, it's just Q1, Q2, right? What about A of 1? A of 1 will be not P1 and Q2, right? And then A of 2 is, so I should visit not P2, Q1, okay? And this is like, So if I have A12, that means not P1, P2, not P1, not P2, right? So it means that the run should visit these things only finitely, this set only finitely often, so not P1, P2, right? And you can make a disjunction over all these, right? And whereas if I consider the standard, the way NSW is defined, right? Non-deterministic. So what is that like? So if I just consider this, so this is the same as like the either for all I, either this is visited finitely often or this is visited infinitely often. Yeah. So this is like not of P1 or Q1 and not of P2 or Q2. Correct? Huh?
And one of those are always there.
Yeah. So now if you just expand this, it's the same as this thing, right? So yeah, you were also right the way you stated. So essentially, like if I consider automata AI of this form, take their union over all the AIs. So this is same as the automata, the given Streett automaton, right? So now what we will try to do is essentially construct for a given I, we'll try to construct the AI. Okay, so we will try to express the AI in terms of a non-deterministic Büchi word automaton, and then we'll take the disjunction over all possible I's. Okay, so if there are k such pairs, then how many possible I's are there? 2 raised to k, right? So let's see if now I think this part should be easy, right? Like what we are saying that you have some subset of these indices, right? Some subset I, and I want to construct the AI. So again, what is the definition of AI? Like you'd like to visit everything for each I, everything in alpha I only finitely often, and every beta I should be visited infinitely often, right? Every beta I should be visited infinitely often. So what can we do here? So what can we do here in order to do this? So all AIs should be visited only finitely often, and all alpha I's should be visited only finitely often, and every beta I should be visited infinitely often.
So like the same copy, if you make a copy of it, then how do you multiply and
And maybe the acceptance rates.
Is that correct?
Yeah, because once it goes to the second copy,
Huh?
there are no alpha I's, so it won't be having infinite alpha I's. And it's going to be accepted only if beta is a zero.
But what does it say? It says that, for example, like if you have, let's say this, okay, for example, you consider I is the empty set. It says that beta 1 has to be visited infinitely often, as well as beta 2 also has to be visited infinitely often. Right? So
Yeah,
what do you do?
The double copy.
by double copy?
By double, you mean like if there are,
K copies.
if there are like, yes, if there are k conditions, then like, I mean, corresponding to AI, at least it's k, that 1 to k minus that I, those many copies you would need. Correct? And then you are going from one copy to the next copy as and when you see an accepting state in that. So if you are in the ith copy, we'll go to the I plus 1, maybe mod k copy, mod kth copy, something like that, right? And in the new copies, you don't have the alpha, the states from the alpha. Clear? So, right? So yeah. So what exactly this is what? So I define alpha I as this, like union over these states. So after the first copy, like you make an non-deterministic transition, and thereafter you don't get to see any of these states, right? So need to visit beta I for all I belonging to this set. And this is similar to like this generalized Büchi automaton, right? This is what we saw. It's similar to generalized Büchi automaton. But we can also directly construct a Büchi automaton, which is like, okay, make this many number of copies of A without the states in alpha, right? So just, I think this is how formally it will be like this. Okay. So essentially, I write pretty much what you said is that if Q does not belong to beta I in some ith copy, then I am in this transition like delta Qi minus that alpha I, because those copies will not have the alpha I cross I. You are staying in the same copy. And if it is if it visits some state in the beta I, because you have to visit, you go to the next copy. So the next copy in that ith, in that in that like set which is in k minus I, right? In the next one there. So that is what I'm defining by next I of that I. Okay, the next I function takes you to the next set, next index in that set k minus I, k square bracket minus I, correct? And then I can say that the set of accepting states is in the first copy. When I say the first copy excluding the original one, which will have these alpha states, right? So the accepting states should not be in this copy, which will have these states. Clear? So you go from this from a copy with the first index in the k minus I to the next, and then you come back, and then I'm saying the minimum index in the k minus I set, k square bracket minus I set. There the beta corresponding to that will be my set of accepting states. Clear? So this is what. So now how many states will then a particular for a particular I, how many states are we going to have in this case? So for a given I, when I'm constructing the AI, this NBW AI, how many states do I have? So suppose initial that A, that NSW, let's say the set of states was Q. So now how many so Q times K, do you really need K plus 1?
Cardinality of I plus K minus 2. Yeah.
K plus 1, maybe.
That plus 1. And K would be cardinality of K minus. So K minus I.
So roughly you are saying like this, something like this.
Yeah. But it would be less than that because we just need K minus I.
Correct. Right? So suppose if you have, for example, let's say, let's consider this case. Let's say here, if your K is 2 and I is 1, 2. So you'd like to visit beta 1 and beta 2, but since your alpha is empty,
K minus 2 minus
just
2.
so it's like only 2 copies suffice, right? One for beta 1 and one for beta 2, right? So similarly, if you consider, let's say here, then the original one and then just one extra copy, right? Here, here you will have the Right, the alpha 1 and the alpha 2 should be visited finitely often. So here just one copy suffices, this one. But what about this one? No, here you don't have anything that needs to be visited infinitely often.
So
This one.
one copy where alpha 1, alpha 2 are also there. Then there should be one more copy where alpha 1 and alpha 2 are there.
Sure, you are right. Yeah, you are right. So this should be visited only finitely often. Correct. So the first copy will have this, and the second copy will not have that. Right? What about this one? Just again 2 copies. Right? So k copies for any of these instances, k copies suffice. Right? So we don't really need k plus 1 copy. Correct? So what I'm saying, if this is equal to n, so if this is this equal to n, right? So then nk copies do suffice. I mean nk states would suffice, sorry, not nk copies, but nk states would suffice. And now how many subsets are there? 2 power k. So nk times 2 power k is the size of the NBW. Okay, it's the size of the number of states you can get. Good. So size of the constructed is nk times 2 power k. Clear? Okay. So any question? Shayantan, do you have any question? Is it clear?
No. Yes,
Okay.
it's clear. Yeah.
Okay, thanks. Good. So let's now look at some lower bound, right? So usually now we have found something which is exponentially larger, right? So is it really necessary? So can we have something smaller NBW, right? Which will for which this exponential blow up is not necessary, and we'll see that this is not going to be the case, in the sense that we'll again construct a family of examples, family of NSW, such that the number of states and the number of these pairs that you have, let's say it's a function of, I mean, it's some n and some function of n and k, right? It's a polynomial in n and k, whereas every NBW which will be accepting that the corresponding language will be exponential in size. Okay, right. And there is one thing to notice here. So we were showing this translation that was from NSW to NBW, right? We are showing this translation from NSW to NBW. And in general, like if you have a non-deterministic automaton, right, that is usually more concise. That is usually more concise, right? In terms of states, usually. Often it's the case that sometimes like you can express a language with a non-deterministic automaton, which may be more succinct compared to an equivalent deterministic automaton, right? Even for the case of NFA, DFA, we know. So if I can show that this lower bound result holds for deterministic Streett automaton, that's even a stronger result, right? I mean, the deterministic automaton can be larger, and then you are having on top of that an exponential blow up, which means that in the case of non-deterministic automaton, you could have possibly even obtained a larger blow up, right? So if you could show such a lower bound on a deterministic automaton, that's even a stronger result. So that's what we are going to show, that we can even have deterministic automaton which are sizes are polynomial in n and k, like n states and k pairs, index is k. It's essentially linear in n and k, but the NBW is going to be exponential. right? So that's a stronger result. Is clear, right? Okay. So again, we'll start with some definitions. So we'll say that there exists a family of languages like L1, L2, etc. Such that Ln, where n is a natural number, can be recognized by a DSW with 3n states and index 2n. So 2n such pairs are there. But every NBW recognizing this language Ln has at least 2 raised to n states. Okay, this is what we are going to show. This is a result like more than, I think, almost 35 years old result. So this is by Moshe Vardi and Shmuel Safra from, I think, this is a stock 1989 paper where they had this lower bound result. So the alphabet is like this. You just have an alphabet of 0, 1, 2, and you consider a word which is in sigma omega, of course. But I'm like looking at the word. When I'm looking at the word, it's like I can look at the word as strings of length n, right? Concatenation of strings of length n, right? So that's how. So these are n length strings like this, right? It's an infinite word, but I'm just kind of, for ease of explanation, I'm considering these as concatenation of n length strings. Now, these are like, these n length strings are like u1, u2. So these are finite strings here. Now I'm saying that an index I, the index can vary from 0 to n minus 1. It is zero active if there are infinitely many j's or infinitely many uj's, right? It's the same, infinitely many j's or infinitely many uj's, such that the ith letter of uj equals 0. Okay, so it's not necessary that at every such for every such string the ith letter has to be 0. That's not necessary. But as long as infinitely many ith position in each of these strings, for infinitely many such strings, you have that the ith position is 0. Then you say that the index I is 0 active. Similarly, we can also define an index I is 1 active. Right? So that means there are infinitely many ith position in these n length strings where the ith position have a 1. Good. Now I'm defining the language as the set of words where the index I is 0 active if and only if the index I is 1 active. Okay. So it's a set of strings where there are infinitely many occurrences of uj's, where you have at, I mean, for every I, like if for infinitely many occurrences of uj's at the ith position you have 0, then there are also infinitely many occurrences of uj's where the ith position is 1. Okay, so this is my language. Clear?
So the uses you are doing is just a random partition.
So I'm just starting from the beginning itself, like, so starting from the beginning itself, like I consider strings of length n, like this. Okay, strings of length n, and I'm looking at the ith position. And this word should be in the language if infinitely many such ith position have zeros, as well as infinitely many such ith position will have 1. Good. So now I claim that the language Ln can be accepted by a DSW, a deterministic Streett automaton, with 3n states and 2n indices. Okay. So can you tell me how 3n states and 2n indices? So let's first of all think about the 2n indices maybe later. Let's start thinking about the state space. So the state space looks like this. It corresponds to some I comma sigma, right? And I'm saying that if it reads a sigma prime from the state I comma sigma, it will go to I plus 1 mod n comma sigma prime, right? So if that is the case, then you see that an index I sigma active, where sigma is either 0 or 1, that's what we have, if and only if the state I plus 1 mod n sigma is visited infinitely often. Clear? From the definition. We saw what is meant by 0 active, or saw what is meant by 1 active. So it is sigma active if I plus 1 mod n sigma, the index I is sigma active. Like at the ith position, you are seeing the sigma. So you will next go to I plus 1 mod n sigma, right? Here I'm saying at the ith position, if you are seeing sigma prime, then you are going to I plus 1 mod n sigma prime, right? So if the state is visited infinitely often, right, in a run.
Why aren't we just saying I? Like
So let's see. So suppose you are starting with some, initially you are in some state, 0 comma, let's say 0, right? Because you are starting with this 0, right? Now you say that, well, I am going to read in this first position. So the positions are from 0 to n minus 1. If I read a 1, right? So then I'm going to have a 1 comma 1 like that, right? But so this 1 corresponds to I plus 1, that mod n, and this is the sigma prime that you are reading, right? So that's the thing. I mean, it's just about the indices, like whether you start from 0 or 1. Clear? Right. So now, is it okay? Like, so this is just the DSW. The transitions are like this. The transitions are simply like this. So I can say, for example, like if I have my transition, this delta n is the transition. So can you now help me how the transition will look like? So the transition will be, let's say, Q. Okay, so I will have I comma sigma prime. This is equal to just I plus 1 mod n comma sigma prime, like this. This is how the transition is defined. Clear? And it's a deterministic, right? It's a deterministic automaton. So we have a deterministic automaton. Now you have to define the acceptance condition such that it accepts this language. So again, what was the language? For every I, right, the index I is 0 active if and only if the index I is 1 active. So now how do you do for one particular I? How do you say that?
I comma 0 is your alpha. I comma 1.
Wait, what?
I comma 0, if that is C, then I comma 1 should be C.
Okay.
And reverse will also be known.
Very good. So I'll just have this. So this is one condition. I mean, like one of the indices. The other one is I comma 1 and I comma 0. Right? So you get two of them for one specific I. And you do this over all the possible. Correct? So this is your that acceptance condition. So how many indices are there now? 2n, right? So for every I, you have 2 indices. So in total, n indices 2n. Acceptance condition. Clear? Good. So one part we have done, which is like there exists, for this language, there exists a DSW, deterministic Streett automaton, which accepts this language, and that has 3n states and 2n indices, right? This is what we have done. Next, yeah.
Hello.
Hello,
Yeah,
yes.
can you explain the transition system once again? I didn't fully get it.
Okay. So what I'm saying is that, so you understood the language, like this language that we are talking about.
Yes, this I have understood.
Okay, so if for every index I, it's like an if and only if, right? So I'm saying that if index I is 0 active, if and only if index I is 1 active. Index I is 0 active, if and only if index I is 1 active. Now the claim is that this can be accepted by a DSW with 3n states and 2n indices. So the states are of this form. It's like 0 to n minus 1 cross sigma, right? So the set of state is of this form. So every state will be of the form I comma sigma. This is an example of a state. Okay.
Yes.
Right. And now I'm saying that from I comma sigma, if you read sigma prime, then you go to I plus 1 mod n sigma prime. Okay, so this actually.
Oh, okay. Yes.
Right. So from let's say the word initially starts with, let's say, 1 0 like this, or 1 0 0 like this. So you start from your initial state, which is like 0 comma 0. Then you read a 1. You go to I plus 1 mod n, which is 1, and then you remember which letter you have read. So you remember that. Next, you read a 0, and then you will go to maybe 2, depends on what your n is. Say let's say your n is 5 or something. And then you remember what you have read, like 0, right? Then again you read a 0, so you will go to 3 comma 0 like this. Is it clear? This is how
Now it's clear. Yes. Yeah.
Okay. And now if this is the case and index I is sigma active, if and only if, so you are reading the index I is sigma active, you are reading at the ith position of that string uj or something. At the ith position of that, you are reading sigma. And this should happen infinitely many times, right? So that means the state I plus 1 mod n sigma is visited infinitely often. Clear? So this is the thing. And then we are defining the acceptance condition. This acceptance condition, it says that if I comma 0 is visited infinitely often, then I comma 1 also has to be visited infinitely often. And if I comma 1 is visited infinitely often, then I comma 0 also has to be visited infinitely often. I mean, this is like this I plus 1. This I plus 1 is the same as this I here. It's just that, right? So for every index I, if this is the case, then it's like the index I minus 1 is like that. This denotes like if this is visited infinitely often, then the index I minus 1 is 0 active, right? If this happens infinitely often, then the index I minus 1 is 1 active, right? And I'm just, instead of I minus 1, I'm just writing I. So clear? Is it okay?
Yes, clear. Yes.
Yes. So this is what we are saying. This is 0 active if and only if this is 1 active. Okay. So now we will prove that indeed every NBW accepting ln, right, it will have at least 2 raised to n steps. So again, a few definitions, right? So first we define something called a relevant position. You can also think of this as a start position with respect to that string uj, right? So this is like, so you have the run, you have like a long run, and we said like you have these uses here, right? And these specific positions in the run, right, from where the uses start, we are going to call it a start position or a relevant position. Okay. Now, we define this string of length exactly n, W0 S, for a subset S of 0 to n minus 1. Okay, so how does W0 S look like? It will have 0 only at those positions, only at those positions in this substring, like, right, in the string, only at those positions which are there in S. Okay, there you will have 0. In the other positions you will have 2. Okay, so the definition of WS0, it's a string of length n. WS0 is a string of length n where a position I will have 0 if I belongs to capital S, the set S. Okay, otherwise, if I does not belong to capital S, then you have a 2 there. Similarly, I can also define W1S. If I belongs to capital S, then in W1S, I have a 1 there, otherwise I have a 2 there. Okay, so now I consider such a string, W0S 2 raised to n and W followed by WS1, and then you repeat it infinitely, right? So this is a finite string of length n, repeated 2 raised to n times, followed by a finite string of length n. This whole thing is repeated infinitely. I mean, repeated forever. Now it's true that W belongs to Ln. Clear? Because like exactly in these positions which are there in S, right? You have the zeros, and so this appears infinitely often. And then similarly, those ones also at the same positions, they also appear infinitely often. Clear? So this word belongs to capital L. Right? And now I'm saying that, so an prime is the NBW that I'm constructing. Okay. And I'm going to prove by contradiction, in the sense that I'm saying that an prime should have less than 2 raised to n states. Okay. And since it's a non-deterministic automaton, an NBW, I'm calling an accepting run. So since it belongs to Ln, right? So this W should also be accepted by this NBW, right? It's a non-deterministic automaton. There, it's possible to have many runs, maybe even more than one accepting run. So let RS be an accepting run of W on An prime. Now, I define again something called an important position. What is an important position? Like, so first of all, it has to be a relevant position. Relevant position. Okay. Suppose the state visited at position P is Q, okay, then there should be another position P prime, okay, another position P prime in the same UJ, right? In the same UJ where the state is again Q, state visited is Q, and oh, not in the same UJ, sorry, in the same sort of like same this part, in the same this part. Okay, like I mean in more specifically in this part. Okay. So I should say that position P prime. Okay, maybe I'll write it in a different way. Where the state visited is Q, and the word between P and P prime is of the form W is 0 raised to some I or L, whatever, like this. Is it clear? Okay, so what I'm saying again, let me just try to write it. So you have
Can we have a discase?
P and P prime, and WS0 is a string of length n, right? Like this, right? So both P and P prime are start positions or they are relevant positions. Okay, and both of them, they visit the state Q. Okay, if this is the case, then I will say that the state Q supports the position P. The state Q visits the position. So the state Q supports the position P. Clear? Again, the definition. The definition is clear. Okay. So I'm saying like our position is an important position. Position P is an important position. If it's a relevant position, so that means it's like you consider the strings of length n, it starts from there. Okay, and there is another P prime which is also a relevant position, and the state visited at both these places is Q. Okay.
So P prime should also be a relevant position.
P prime should also be a relevant position, right? Okay. Now, I claim that QS, suppose now I'm defining QS, is a set of states Q such that Q supports P for infinitely many positions. Okay, it's a set of such states which supports P for infinitely many positions. Yeah, infinitely many positions P. Okay, so I'm saying QS is such a set of such states. So I would like to say that QS is non-empty. Why is it so? I would like to say QS is non-empty. So what is again QS? Like
the number of states are n. So like since these are like 2 per n such keys are there, there will be some repetition. So but why will they keep appearing again and again?
Right. Why will they keep appearing again and again?
They could, but they need it.
Yeah, but I'm saying that they need to be. Right. So first of all, you think of a single such block here, right? A single such block WS02 raised to n, single such block, right? So there will be some state which will be there, correct? So some states will be repeated because it's WS02 raised to n, and you have like how many such 3n states are there, right? So 2 raised to n is much larger than 3n. So some states will be repeated, correct? And
the repeating states are also gonna be like.
So there are only finitely many such states which can get repeated in each block, and there are infinitely many such blocks. There are infinitely many such blocks, right? And there are only finitely many such possibilities which can get repeated in this infinitely many, right? It's like a pigeonhole principle being applied twice, right?
So there will be
Some
state that has to repeat, like, right? So essentially, which says that this QS cannot be empty, right? Okay. So if you consider one such block, there will be some finite number of states which will support the position P, right? And there are infinitely many such things happening, and you have only finitely many choices. So some will get repeated infinitely many times, right? So the set of such states such that Q supports P for infinitely many times, this QS is non-empty. So now the remaining part, I believe you can do yourself. So consider now two different such sets. S, what was capital S? It was a set of such indices like between 0 and n minus 1, set such numbers. You consider now another set which is capital T, which is different from S. Okay. And QS is such capital Q which supports P for infinitely many positions. And similarly, you can also define QT, right? QT. So corresponding to T, you will have another word, right? If I call this WS, corresponding to capital S, I can have a WT, right? Right? And I can define QS, I can define QT, correct? I can define QS, I can define QT like this. And now I'm claiming that if S is not equal to T, then QS and QT should be disjoint. Proof by contradiction. Suppose QS and QT are not disjoint, then what? Suppose QS and QT are not disjoint. So if QS and QT are not disjoint, then there exists some Q. Okay. So let's see. Proof by contradiction here. Suppose QS intersection QT is not equal to empty. So that means there exists some Q such that Q belongs to QS and Q belongs to QT. So what does it mean? It means that Q supports P for infinitely many positions, P in that run corresponding to WS, and there is also the Q which supports P for infinitely many positions at infinitely many positions P in the run, in an accepting run corresponding to WT, right? So you have, let's say, the corresponding accepting runs. I call them, let's say RS and RT like this. Okay, so that's the thing. So then Let's see if we can. So can we say this, that by the definition of that important position, right? So you are going from Q supports P, right? Q supports P. So Q on some WS0I, you are reaching Q. And Q on some WT0I prime, you are again coming back to Q. Clear? Now, I'm just saying something and try to see how we reach the contradiction. Just think about this. Now, I am claiming that wherever, so what is happening, like, so there's the state Q, you come back here WS0I, and you have another sort of run here WT0I prime. What is the word that we started with? The word W. The word W is of this form. WS0 to 2 raised to, sorry, 2 raised to n, then W1S, right? And then we are repeating this omega, right? And we have the accepting run corresponding to this RS, okay? RS. Now what can we do? Can we modify this word?
W0 power I1, WT0 power I2, WS0 power I3, WS1.
So what we can do is essentially, like, we can inject some of these things in this word. So wherever it, so what does it mean? While reading this, sometime it comes back to at different places. Like it is coming back to this Q by reading some number of I's, right? Like from some, when I am looking at this run, let's say, it may happen that from here to here, it reads WS0I, okay? From here to maybe again, after a while, it comes back here, right? From somewhere, from here to here, it comes back. And maybe this time it read WS0, maybe I2 or something. It can happen, that can happen. But every time it comes back here, I am now injecting, I'm now reading this word from here, WT0I prime. I'm reading this word here, I prime. So if I do this, and if my original RS was accepting, I can still get an accepting run while reading this word which has this injected WT0I prime, right? I can still get an accepting run with these words, right? So the word that I'm getting by modifying this W, by injecting these things, it is accepted by A prime. So this word, the new word, let's say I call it W prime, that I get by injecting these infixes, belongs to L of A prime. A prime was the NBW that we were constructing, right? The question is that, does W prime belong to the language LN? Why not?
Because the WT0 will only have 0 and 2. But our condition is like when 0 is repeated, we want 1 to be repeated. So say like the position, there is a position like we are assuming T is S is something T minus S is non-empty.
Okay, so good. So let's say you are right. So let's say without loss of generality, so we said this, right? That T not equal to S, right? This is what we said. And I'm saying without loss of generality, let's say t minus s is not empty. So there exists a position I, right? There exists a number I between 0 and n minus 1, which belongs to t but not in S. Now that position gets here, that position, like in this string, which has these injections, the modified string W prime, that position will have infinitely that position will have infinitely many occurrences with zeros because of this thing, right? Clear? Okay. But that position is not going to have infinitely many ones. What do you mean?
It will not get one in any of the occurrences because W is 0.
No, you have ones here.
But in that position, it won't have.
In fact, that position, it will not have any one at all. Is it clear? Not really? Okay. So suppose, okay. So this was the string, okay? Let me write this again. So this was my string to start with, right? Now what is happening? So I'm saying that we are going to prove the following, that for S not equal to T, QS intersection Q2, QT is empty, right? So suppose by way of contradiction, this is non-empty. If that is the case, then there should exist some state Q which belongs to QS and which belongs to QT. So if Q belongs to QS, what does it mean? Q supports P, some relevant important positions P, at infinitely many such positions P, right? And Q belongs to QT, it's like the same, but now the word is different in the sense like in an accepting run where it's like a T here instead of S, right? Now, when we say by the definition that it supports, Q supports P, that means there exists a position here P, here there is a position P prime. Between them, the word being read is WS0, some repeated some I times. Similarly, here Q supports P at infinitely many positions in the run corresponding to the corresponding to this WT, right? Corresponding to that. So if this WT0 is repeated some number of times, so let's some I prime number of times, right? And Q comes back to Q. Q being common in both QS and QT. So this also happens, this also happens, right? So now you consider the run RS corresponding to this W, okay? Just for the sake of understanding, I call it WS. So the corresponding accepting run we started with, it's RS. So it's like this. So the Q is appearing from here to here, some WS0 I times it read, just this. Maybe again somewhere from here to here, it again read some repetitions of WS0, right? Now every time it comes back, whenever it's at Q, I am also reading this WT0 that I prime, right? Because I had this thing. I'm also injecting this word. So I'm now modifying the word. I'm modifying the word such that at such positions where it comes back to Q, I'm also injecting such infixes in that string infinitely many times, right? Wherever. So I get a new word, W prime. Now you consider the original run RS corresponding to this word WS, the original without the injections. That run was an accepting run. If I inject these things, it will still be accepting, correct? Now, so it is, this word is still being accepted by the NBW. Now, what I'm asking you to think, does this modified word, which is this W prime, where I injected this infinitely many times, does this belong to the language ln? What was the language ln? For every I,
0 and 1, in the position I is 0.
Active?
0 active, if and only if it is 1 active.
If and only if it is 1 active. Now this position is 0 active.
It's where S and T differ.
The place where S and T differ. So now this extra position which is there in T, sorry, this extra position there which is there in T, there the zeros are appearing infinitely many times, but ones are not appearing there infinitely many times, right? In fact, not even once. Hence, this modified word is not there in the language, but it is accepted by the NBW A prime. Hence, there is a contradiction. So, our claim that this is QS and QT are not disjoint, this claim, like, I mean, this is false. So this claim is true, that indeed they are disjoint. QS and QT should be disjoint.
Now there are 2 to the n many subsets. So
There are 2 to the n many subsets.
exactly.
So if every pairwise they are not, they are not overlapping, that means if pairwise they are disjoint, that means there should be at least 2 raised to n states in the NBW. That's the proof. Good. Right. So let me see how much I can continue. So now we are going to look at the decision problems. Okay. So essentially what we are going to look at is the complexity of these decision problems. Okay. So what complexity classes we are going to use? So I would assume that you are familiar with these classes. If not, I will just say briefly what they are, and then you should study them yourself. Okay, and then I'm also going to talk about, use some theorems in order to talk about some of these things. But seems like I may not be able to finish, but I will continue in the next next class. So we are going to talk about NL, which is also called sometimes n log space, the same as n log space. Okay, so are you familiar with these classes? Like, have you have not done a complexity theory class, you have done a complexity theory class. So we are going to use P space, right? And also NP space. We are also going to talk about co-NL. Okay. What is the difference between P space and NP space? They are the same actually, right? But it requires a proof, which you will study in your complexity theory course. Right? This theorem is called the Savich's theorem.
Even NL and co-NL
Are the same. But we don't know about NP co-NP. NL co-NL are the same, yes. And what is that theorem called? NL co-NL? That also requires a proof.
there was some, is there a path in a graph, that kind of problem?
That is called, I mean, it's an NL complete problem.
And that's also co-NL complete, so like that.
Mhm.
And that's why both the classes.
So this theorem is called the Immermann-Zelepsini theorem, okay, which shows that NL is the same as co-NL. And the way, I think the original proof of Immermann, so these were different, independently they came up with these results. And the original proof of Immermann goes through logic, and it uses an area called descriptive complexity. And he has a book an entire book on this thing called descriptive complexity. So yeah, I mean, if you want to look at the proof, you can read his. I mean, it's a couple of pages possibly in his book. That NL equals to NL. It's a very nice, elegant proof. Uses these things. Okay, so we are going to look at this decision problems. So what is the non-emptiness problem? Yeah. Okay. I mean, we are not talking about the emptiness, but we are talking about non-emptiness. Okay. But well, I mean, they are almost the same in the sense of like complexity and we'll see. So we are talking about the non-emptiness problem. We are also going to talk about non-universality problem. What is the non-universality problem? Yeah. So that is like, so how are non-emptiness and non-universality related? Okay, so if an automata is non-empty, or if an automaton is empty, if and only if its complement automaton is universal. And it is non-empty if and only if its complement is non-universal, right? What is the language containment problem? Okay. Can you think of the universality problem as a sort of like a special case of the language containment problem?
Just when we check if LFA is LFP and LFA is the automata which accepts all universal.
Right. So the thing is, like, we are asking the question that is A universal? Is the same as asking is sigma omega subset of L of A, right? So the universality problem is a special case of the inclusion problem. Okay. So universality reduces to the inclusion problem. Okay. Universality reduces to the inclusion problem. So in fact, for some complexity class C for some given kind of automaton, if this problem is, let's say, C complete, then this problem is C is a complexity class. If this problem is C complete, then this problem is what? Sorry, I didn't.
First one is the special case of the That's hard.
It's C hard. Right? If the first problem is C complete, then the second problem is C hard. Right? So you should maybe revisit the definitions of hardness, completeness. I mean, you understand, of course, but like, I mean, maybe just okay. So this is this. So now the non-emptiness problem for NBWs, it is decidable in linear time and it's NL complete. So what is NL? Non-deterministic log space. So first of all, like, given a non-deterministic Büchi word automaton, just forget the theorem, okay? So how can you check its whether it is empty, the language accepted by this automaton is empty or not? From an initial state, from some initial state, whether a good state is reachable, and
can we come back to it state?
Right.
From a good state, you should come back to
another good state.
Yeah, that
won't be fun because from there we have to check it.
okay.
So eventually we can reach a good state and then ensure we visit.
There should be one good state that is reachable from this.
Sure. And
as its time.
And should be reachable from this.
Sure, from some initial state, right? So there should exist, so there should exist some Q belonging to alpha, such that there exists some Q0 belonging to capital Q0, such that from Q0 there is a path that goes to Q, and from Q you can come back to itself. Clear? So this is what we need to do. So why is it in NL, non-deterministic log space? What can you do? So how can you give, first of all, okay, no, maybe the linear time algorithm may be a slightly more difficult, but okay. I mean, I should double check this whether it is linear time, but even if it is, you say, let's say it's in polynomial time, we are still in P like that way, but.
Like the products and then we can just guess a Q which satisfies this property and also guess the path and the cycle. And then we just have to verify if that path is actually valid or not by looking if there's actually a lens property.
Yeah, pretty much like that. So what you can do is so you start, you guess some Q0. So guess a Q0 and a Q. So this is like my source, this is like my target. And then you kind of guess the next states, the next vertex in the underlying graph starting from Q0. And then you have to reach that Q, and again starting from Q, you do the same thing and you say that I would like to come back to Q. Now, if I just say that, there is something which is missing. What is missing? There is something which is slightly missing. So I say that, okay, you start from guess the Q0, you guess the Q. I just go from Q0, I guess the next vertex, guess the next vertex, guess the next vertex. No, I mean, I'm guessing it correctly if it exists, and I'll end when I reach Q. When I reach Q, right? But what is as far as the NL is concerned, what can go, I mean, what is not fully specified here?
That we can check if there's a valid transition between any two.
What is to do with the non-deterministic log space? So I'm guessing the next vertex. I'm guessing the next vertex. So where is the log space coming in this whole business?
Oh yeah. So we will terminate once we are sure that we have visited a path of length greater than n. Because it's always
path of length not greater than at most n. Yes.
Because it's always possible that there is no such Q. So whatever we guess is not going to lead us to anything.
Right. So the thing is that when I'm doing this thing, so I'm going to store in my algorithm. So I guessed this, I guessed the Q, and also I'm going to guess the next vertex. So at any point in time, I'm also storing a current vertex I am in, right? So this I need to store. I need to store oh, this is where I am in, and I'm going to guess the next vertex after that, right? And I also should store a counter, right? At every point I increment my count, and then when I reach, if I see that my count is exceeding n, then I will say that I'm not reaching that Q. I should reach that Q within n steps, right?
Then we'll go by a different path.
No, the thing is that it's a non-deterministic machine, log space. So if it exists, then you will choose the right path. You will have the ability to choose the right path. Okay.
Then we won't have that if we can choose.
Yeah, you choose the right path. And the non-deterministic machine always, I mean, it can choose the right path if it exists. But then this verification part is okay, like to say that indeed I can do this within n steps, and for which I maintain such a counter. Okay, the counter value will become at most n. Okay, so at most n. So all these things, so the counter value being at most n, I can store this in log n bits, where n is the number of states, right? The current vertex, if I have n many states, every vertex can also be represented with log n bits, right? Log n bits. The counter value can be stored with log n bits, right? I'm guessing this Q0 and the Q, the initial state and the final state. Everything can be done with log n bits, right? And coming back from Q to Q, again, there is a path of at most length n, again log n bits, right? So everything, so this non-deterministic machine can do everything using log n amount of space. Hence, it is in NL. Okay, right? So that is the NL algorithm. Okay. Right. So here, what I was saying is that, like, exactly what you said, that where these parts that these parts that I wrote here, like this thing. So this is what I was trying to prove a bit formally. Like, if LA is non-empty, then indeed you can find such a queue such that starting from the initial, this thing you can go. So if it is non-empty, then what does it mean? That it means there exists a word such that this word starting from the initial state, it will go to some final state like this, and from there it can like visit this. Some state will be visited infinitely often. Some good state will be visited infinitely often, right? And you can reach that good state from your initial state, and then you can keep looping, right? So that is what. So if L is non-empty, if the language is non-empty, language of A, then you can indeed find this. And the conversely, like if you can find such a thing, like that you can reach from the start state to a state which is a good state, and if you can visit that like from itself, then you can also see the labels, right? The label, and you can construct an infinite word, and hence LA, the language of A, is non-empty, right? And we looked at this thing, which is that this is the NL membership. NL membership. What about NL hardness? Did I have? Okay, yeah, I have already. NL hardness. How do so there is this NL complete problem. It's a very canonical NL complete problem from which we will do the reduction. So let me just write this, and we'll go over this and we'll stop. So the reduction from the reachability problem in directed graphs. Okay, so you are given a source and a target, and then you are asked the question, in this directed graph given a source and a target, can I reach from the source to the target? This problem is known to be NL complete. It comes under various names. Reachability in directed graph, some people call it ST-con and so on, ST connectivity and so on, right? Now, how can you reduce it to
So your S will be one of your start states, T will be one of your good states. And then after that, T will be one of your good, S and T will be the same, which is one of your good states.
But you may not be, this graph may be some kind of a finite graph, maybe like you may not have a loop or cycle or something.
Okay, we can do this first. S is the starting state, T is one of the good states. If we get a path, then both our S and T will be the same. And then we will get a path.
Sorry, what? So I'm saying that so what I want to do is, like, if there is a given this graph, I would like to construct a non-deterministic Büchi word automaton such that if there is a path from S to T, so there is a path from S to T, or the Büchi automaton will be non-empty if and only if there is a path from S to T. The Büchi word, the non-automaton will be non-empty if and only if there is a path from S to T.
So T will just be one accepting state in that automata, and there will be a self loop.
Yeah. right? So is it okay? So you can just, so the edges in the graph, I'll keep them as is in the automaton, right? I'll put some labels there, maybe just some A on every label. Every edge, I add a label A, and then on the T, I just add a self loop, extra self loop. Okay.
Oh, okay.
So what does reduction in general do? Given an instance of a problem, so if I'm doing a reduction from problem A to problem B, just general reduction, like independent of the complexity, right? So I'm doing a reduction from problem A to problem B. So it is like I have an instance of problem A. Here the instance is a graph, a given graph. So that is an instance, right? Here it's a graph. I am constructing another instance, which is the automaton, right? And what is this problem? This problem is about the reachability from S to T. This problem is about non-emptiness. If this is reachable, if T is reachable from S, then the instance, the automaton instance that I have constructed, this should be non-empty, and it's an if and only, right? So this is what we should do. Like I can construct any automaton of my choice, okay? As long as this is like, yeah, this, if T is reachable from S, then this should be non-empty and vice versa.
So essentially, S is the only initial state, T is the only good state, and then the
Yeah. Right? Absolutely. Right? So that is this. So yeah. So if you have G equal to V, right? And just tell me what is the automaton. I have this is an NBW. So I have V. I just have a single letter. The alphabet has a single letter A. Then I have a single this thing S. And I have a delta transition. I have T, right? So this is my automaton. And I will say that, yeah, sorry, I'm going a bit out of time. So I'll say the delta of V1 A equal to, yeah, E of, yeah, set of all V2 such that E of V1, V2. And then also I have delta of T comma A, right? So this is the automaton.
T union E of, but doesn't, okay.
Yeah, because this is already covered here. What you are trying to say.
Right? So once it reaches T,
I mean, you were right. This T union, like, you were right. Like,
but it doesn't matter, right? Because as we just want to see if it's.
So that's actually, yeah. Okay. Yeah. Yeah, I mean, yeah, I should write, maybe, yeah, just to be uniform, like, I mean, T union, like, V such that E of T comma V volts, something like that. Okay, good. So you can think of the deterministic algorithm. I'm not going to take more time, but like just how you can get a deterministic algorithm. I need to check whether it is surely linear time. Maybe it's, but certainly polynomial time from quadratic or something you can certainly get. And instead of, so here we have made an NBW, you could have also made a DBW, deterministic automaton. What will be the change?
Just make the alphabet size larger.
The alphabet size larger. So the largest out degree, something like that. right? The alphabet size can be the same as the largest RTP. Okay, so good. So I'll stop here. So any question, Shantan? Do you have any question?
No, it's clear.
Oh, so I'll just stop